Okay. All right, so everybody paying attention here? We really need to get through some of this stuff. So I think I am going to skip down and start with problem number 3. All right, problem number 3. In my notes, section 9.5. Number 3, find the sum. Now, I am going to list my sum formulas over here, and I think it was at the very end of the period I wrote these down. Did we talk about what they are used for? Remember, you do not need to memorize the formulas, but you need to know which one to use to do problem number 3, which is find the sum of these terms. Now, I know you could type those in, add them up on your calculator, but what if there were 300 of them? You wouldn't want to do that. So we're going to practice with our formulas. Even though there may be times you choose not to use a formula, and that's okay as long as you're showing your work. What kind of a sequence is this? What kind of set of numbers is that? Arithmetic with a common difference of 4. Now, of the formulas that we have over here, only one of them is arithmetic, and it's this one. There should be no confusion in your mind. See that R? See that R? R stands for common ratio, and common ratios are geometric. So this is my arithmetic formula. All right, N is how many terms I have. Well, how many terms am I adding up? 6. So 6 over 2. Remember, every N is the same, so it's all 6 in this problem. So 6 over 2. A sub 1 is the first term. A sub 1 means term 1. And then A sub 6 means term 6. So the sum of these looks like it's going to be 18. Is that okay? Now, if there had been 300 of these terms, a whole bunch of them, it wouldn't have been any harder, right? So that's the beauty of the formula. It doesn't matter how many there are, it just, you just do it. All right, what about the next one? Here's this set of numbers.
Don't you subtract the A and
What am I doing here?
on the first problem? Don't you subtract that 13?
No, the formula, oh, that's supposed to be a plus. Oh my gosh. Thank you, Abe. That's supposed to be a plus. That's a plus. I wrote that wrong. Make sure you fix that. Should have had those written down from Friday. Look at Friday's notes. Did I do it right on Friday? Or Thursday or Tuesday, whatever day that was?
Yeah.
Okay. Yeah, that's a plus. That's a plus. Thank you, Abe. All right, now, what's happening here? Arithmetic or geometric? Arithmetic, and the common difference is?
-7.
So I'm going to use the same formula. Uh-oh. There's a bit of a problem. Does anybody see what the problem is? I don't know how many there are. I know where I start and I know where I end. So in terms of my formula, I know that my first term is 117 and my last term is 33. So I can do that part of the formula, but I don't know this number. So when that happens, you can try to figure it out, and that figuring out is fine. Figuring it, logic is fine. You can also always go back to your other arithmetic formula. Your your other arithmetic formula will give you the information that you need. Here's how. The last term, I don't know what n is, but I know that's the last term, is the first term plus the common difference times n minus 1. You see how that's going to tell me what n is? So my first term's 117, my last term is 33, my common difference is -7. I just plug all that in. Now I'm going to figure this out. Now this won't be the answer, but this will be n. Did you get 13? Anybody? Yeah, and it's 13, Jake?
Can you remember, or memorize all these formulas?
Nope, I already said that.
Okay.
You need to know when to use which one.
Yeah, yeah.
But I'm gonna give you the formulas.
Okay,
Okay, anybody else get 13? Okay, so now we know n, so we can come back here and put it into the sum formula, which this was our job. Our job was to find the sum. So the sum of all those is, I got 975. Is that okay with everybody? All right, let's do one more of those. Let's do letter C. So erase my formulas and get one over them, but you got them there, so you're ready to go. All right, so here I'm gonna add these up. What do you notice about this set of numbers? It's geometric and the ratio is times 3. Now, because it's geometric, I will be using my geometric sum formula. I know that the first term is 5, and I know the ratio is 3. But just like a minute ago, what's the problem?
You don't have it.
I don't have n.
Well, we can find it.
You can find it, you absolutely can find it. And you can find it by, if you want, you can just keep timesing by 3 and count up how many times it takes. Or we can go back to our other formula, our geometric formula, just like we did here, only that was arithmetic, and plug in what we know. The last term is 98415. The first term is 5, and the ratio is 3. Now that equation is a little scarier than this one was, for sure, but you don't have to solve this. We did it back in chapter 3. What's step 1? What do we need to do first? Divide by 5. So 98415 divided by 5 is 19,683 equals 3 to the n minus 1. Now, if we found this problem laying out in the hallway out of context, I would absolutely insist that you use logarithms. This is a logarithm type problem. So if you get that, if you know how to use logarithms, you're comfortable with logarithms, then do it. That will always work. But in this particular case, would you agree with me that n has to be a whole number? Remember what n stands for. N stands for the 20th term or the 50th term or something like that. So it doesn't have to be a whole number. And that means that this guy right here is 3 raised to some power. So if you don't want to use logarithms, you can just take your calculator and do some trial and error, like what's 3 to the 10th? Well, it's too big, so what's 3 to the 9th? Oh, number right here is 3 to the 9th. Just trial and error on my calculator. So if 3 to the 9th equals 3 to the n minus 1st, then what does n have to be? 10. So again, that's kind of a sneaky little thing, but it's absolutely okay because I know n is going to be an integer. I know it is. It has to be. So I can just play around with it till I get the number. And you know this. Then I gotta type this in. I like to make this a -2 on the bottom first, 1 minus 3. Ooh, I got 147,620. Anybody else get that? Those are a little tricky to type in, so make sure that's what you got. You okay with that? All right, let's try a couple in this next section, number 4. Find the sum of the first 90 terms of this sequence. So we've got this sequence, and we want to find the sum of the first 90. This is problem 4A. What formula? What kind of sequence is this? Arithmetic with a difference of 3. So my formula says 90 over 2 times what goes here. First term, -2. Oh, shoot. What's supposed to go there? The last term, the 90th term. Guys, look at your formula. If you're not gonna memorize them, which is okay, you gotta know how to use them. If n is 90, what goes there is a sub 90, which is the 90th term in the list, which I do not know. So what am I gonna do?
You're gonna find it.
I'm gonna find it. And how am I gonna find it? I'm gonna do what I just did a minute ago. I'm gonna use my other formula, my other arithmetic formula. If you don't have enough or the right information for the formula you need to use, then try the other one and see if it will give you what you need. So according to this formula, the 90th term will be what? The first term plus 3 times 89, n minus 1. $265. Now that is not the answer. What do I do with that? That's not the answer.
Plug it in.
That's what comes over here, right? And then I can get my answer, which is 11,835. Okay, let's do the next one, B, 4B. Directions say find the sum of 12 terms. Okay. What kind of sequence is happening here? And we're multiplying by 2. So my formula is this one. So that'll be my first term minus my first term times my ratio to the 12. Oh, this is okay. I got it. I got what I need, right? I have everything. So I would definitely make this a 0.9 before I started. Type in your numerator, type in your numerator. It equals, and then divided by 0.9. Did you get negative 455? Oh, no. Oh my gosh, you guys, this is a bad day for me. What's that denominator supposed to be?
Miss Four, you don't have any bad days.
Oh, yes, I do. Today's a bad day. I made 2 mistakes in like the last 20 minutes.
Yeah, those happen.
Gosh, that's a sequence. At that rate, we could figure out how many I'll make by the end of the day.
I think we should go to lunch.
0.1 minus 0.1 times 2 means we shouldn't go to lunch at all. Divided by. This looks better. I knew that answer bothered me. 409.5. How does that look? That I think is better. Remember, your denominator is 1 minus your ratio. So, yeah, now I got it. 1 minus your ratio. Alright, so of the formulas that I listed on the board at the beginning of the period and the other day, we haven't used this one yet. This is our infinite geometric series. This is the formula that we use when our sequence goes on and on and on. Now I know this one that we did earlier, it has a dot, dot, dot at the end, but those directions said find the sum of 90 terms. We just didn't write all 90 out, but it said 90, a specific number. So that's why we used one of those formulas. This one is going on forever. There is no ending point. This is the formula we use when it's infinite. 2 things about this formula. First of all, since there's an R, this sequence has to be geometric. And second of all, the ratio has to have an absolute value less than 1. Now, think about this for a second. I am asking you to add up something that goes forever and ever and ever. If the terms were getting bigger, so for example, if we had this sequence, would it be possible to add that? No, because they just keep getting bigger and bigger. The only way you can add them, infinitely add them, is if the terms are getting smaller. The number that you're multiplying by has to be less than 1. So, in our problem, 5a, what am I multiplying by? Problem 5a. What am I multiplying by here? A half. Therefore, because that's less than 1, I can use my formula and add these up. So the formula says, take the first term and divide it by 1 minus the ratio. You can use a calculator to help you with all the arithmetic. The sum of those, if we kept going, just kept adding, we'd eventually get to 6. Well, you'd be older than me when you got there, but we keep getting closer and closer to 6. Okay, just a couple more things. Let's do one more of those. Let's look at problem B. It's an infinite series, so I want to add these up. The formula says take my first term over 1 minus the ratio. Now what am I multiplying by here? 1/2. So I got 8/3, but yeah, I could be totally wrong because I made so many mistakes today. I got that sum to be 8/3. That is a very easy formula to use. Very easy. But it does have that one tricky thing. Look at problem D. Problem D is not addable. Because what we're doing is multiplying, I think, by one, let's see. Yeah, we're multiplying by 1.5 in problem D. And the terms have to be getting smaller, so D would have no answer. You can't sum that one, because the terms are just getting bigger and bigger and bigger, and they have to be getting smaller. All right, your very last pre-calculus notes, I think.
Let's go!
I know, it's kind of sad, kind of sad.
Nah, it's cool.
We're gonna write this as a fraction. Okay, we're gonna write this as a fraction. Now, you know that bar over that means it's repeating, right? So, there are lots of ways to do this. As long as you show your work, I couldn't care less how you do it, as long as you show your work. But I wanna show you why that problem is in this section of your textbook. This means 0.444444 infinitely, right? I could break this up and say it's 0.4 plus 0.04 plus 0.004. Now just think about that for a minute. If you added these decimals, isn't that what would happen?
Yeah.
This is an infinite geometric series because I am getting from term to term by multiplying by 0.1 or dividing by 10, adding a decimal point, 1/10. So the sum of this will be the first term, which is 0.4, over 1 minus the ratio, which is 0.1, or 0.4 over 0.9, which is 4/9. Now you might have remembered, especially, I don't know if any of you had Mrs. Field, she does this all the time in Algebra 1. We know that a regular 0.4 is 4/10. 0.4 repeating is going to be 4/9. That's how it works. So 0.1 repeating would be 1/9. If they repeat, they're over 9 instead of 10. Now, that's all cool until we get something, last problem we're gonna do, like C. What is wrong with problem C? It doesn't all repeat. So, not all of that whole number. You can write this number as 0.1 plus 0.04, 0.004, and so on. That's fine. But this is not part of the sequence. So you can add up this part using your formula, but then you will have to go back and add in the 0.1. All right. My formula says first term, and the first term I can add is 0.04. My ratio is still 0.1 because aren't I just adding one extra zero as I go down the line? That's like dividing by 10 or multiplying by 1/10. So this is 0.04 over 0.9, which is 4/90ths. If I move the decimal point 2 places. Now take that 4/90ths and add part of the number that wasn't included in the sequence, so 1/10. So we get a common denominator. And it looks like 13/90. Just for fun, what's 13/90 on the decimal line on your calculator? Yeah? Yeah, it is. So you can change any repeating decimal into a fraction using this strategy. Just remember that the formula will only work on the repeating part. And then you have to go back and add in whatever wasn't repeating.
You forgot an extra 4. You started with 0.14,
Well, but does it really matter?
Yeah, no, it's still the same number,
Yeah.
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 I'm just trying to get you another mistake for
No,
that.
no, I did that on purpose, no. That's not very nice, by the way. All right, I want you back at 48. Everybody back at 48.